guys, welcome back to my YouTube channel. Today I am going to solve day 28 problem of this month on Leetcode. Before starting, if you guys haven't subscribed my YouTube channel yet, then please go ahead and subscribe it. Now without any delay, let's get started with today's problem. So today I am going to solve problem number 2045, that is second minimum time to reach destination. Okay, so let's read the problem statement first. So a city is represented as a bidirectional connected graph with n vertices where each vertex is labeled from 1 to n inclusive. Okay, so if n value given to us is 5, then simply means we have cities from 1 to 5. City 1, city 2, city 3, city 4, city 5. Okay, inclusive. The edges in the graph are represented as a 2D integer array edges where each edges of I is equal to u of I and v of I denotes a bidirectional edge between vertex ui and vi. Okay, so this is just a bidirectional edge. Okay, so let's say there are two vertices 1 and 2. Okay, if both are connected, I can represent it like this, and by bidirectional I can simply means we can represent it like this only, right? 1 and here like this. Okay, so that's a simple meaning of bidirectional. Okay, so I'm going to represent it like this. Okay, every vertex pair is connected by at most one edge and no vertex has an edge to itself. Okay, so you will not find such cases. Okay, the time taken to traverse any edge is time minutes. Okay, so 1 to 2 if I want to go, so then this is the time that I'm going to take. Okay, time minutes. Each vertex has a traffic signal which changes its color from green to red and vice versa every change minutes. Okay, so we have given one change value. Okay, and traffic signal is going to change after every this change minutes. Okay, so let's say if change value is equal to 5. Okay, so I'm saying that if my change value is equal to 5, so let's see this line. Okay, so this is at time interval 5, then again one more time interval 5, then one more time interval 5. Okay, just like this. Okay, so initially all the signals are going to be green. Okay, after 5 minutes my signal will turn to red. Okay, then again after 5 minutes my signal will turn to green, then again after 5 minutes my signal will turn to red. Okay, so this is given to us. All signals change at the same time. You can enter a vertex at any time, but you can leave a vertex only when the signal is green. Okay, you cannot wait at a vertex if the signal is green. Okay, the second minimum value is defined as the smallest value strictly larger than the minimum value. Okay, so see this example. So this is smallest and this is the second smallest. Okay, so 3, so output is 3, and this is strictly larger, right? So here see this example, 2 to 4. So in this case output is 4, right? Two persons have same height and we have to find the second smallest now. So this is going to be my output. Okay, if for in the list of these peoples. Okay, so strictly larger, right? So we have given n edges, time and change. We have to return the second minimum time it will take to go from vertex 1. Okay, so here vertex 1 simply means this is going to be our source to vertex n. That simply means this is going to be our destination. Okay, so in problem statement it is given that my source is a city 1 and my destination is city n. Okay, so you can go through any vertex any number of times including 1 and n, and you can assume that when the journey starts all the signals have turned green. Okay, so from this problem statement one thing is clear, that we are moving towards the Dijkstra's algorithm. Okay, which is nothing but our shortest path algorithm. Okay, single source shortest path algorithm. Okay, so it is used for solving single source shortest path problems having no negative edge weight in the graphs. Okay, the Dijkstra's algorithm. Okay, so I'm just going to give a little bit quick recap about this Dijkstra's algorithm, then we directly proceed with the example number 1. Okay, so how this algorithm works. So in initialization, so in this we are going to set the distance to the source node to 0 and the distance to all the nodes to infinity. Okay, and then we are going to mark all the nodes as unvisited and set the source node as the current node, and we are going to create a set of the unvisited nodes called the unvisited set, which contains all the nodes. Okay, then we are going to iterate. Okay, so for the current node we are going to consider all of its unvisited neighbors. Okay, and then we are going to calculate their tentative distances through the current node, and then we are going to compare the newly calculated tentative distance to the current assigned value and assign the smallest one. Okay, so this is what we are going to do. Like in this example, let's say if current node is A is marked with the distance of 6 and the edge connecting it with the neighbor B as a length 2, okay, then the distance to B through A will be 6 plus 2 8. Yes, okay. If B was previously marked with the distance greater than 8, then we are going to update it to 8, otherwise we are going to keep the current value. And after considering all the unvisited neighbors of the current node, we are going to mark the current node as visited and remove it from the unvisited set. A visited node will not be checked again. Okay, then this is the selection. We are going to select the unvisited node that is marked with the smallest tentative distance and set it as the new current node, then go back to step 2. Okay, this one. Okay, so the algorithm continues until the destination node is marked visited, okay, when planning a route between two specific nodes, or until the smallest tentative distance among the unvisited nodes is infinity, which happens when there is no connection between the initial source node and the remaining unvisited node. Okay, so now let's understand this with one textbook example. Okay, so in college you will see this example definitely in your textbooks. Okay, so here see, let's say I'm starting from this vertex, okay, 1. Okay, from this, so now from 1 I have path to 2, right, and the here see distance is 50. Okay, so here I'm just going to fill initial values. Okay, 50. Then from 1 I can move to this 4, right, with the distance as 10, right, here. And from 1 I can move to 3 with distance as 45, right, so here I'm going to write 45. Then from 1 can I move to 5? Direct, I am finding direct path. No, there is no direct path from 1 to 5. Okay, so here I'm going to write infinity. Then 1 to 6 I can move? No, so I'm going to write infinity. Okay, then after that what we need to do here? Then after that we have to find the smallest value. Okay, so smallest value is available at which position, at which node, at which vertex of this 4. Okay, so this 10 is a minimum value, right? So now I'm going to visit the neighbors of this 10. Okay, this node 4. Okay, so here I'm going to write selected vertex as 4. Okay, so I have selected the vertex as 4. Now from 4 I can move to 1 and I can move to 5. Okay, so if I move to 1, then I am getting the cost as, okay, 4 to 1 I need to move. Okay, but see, 1 I have already selected now. From 1 I am starting now, so I'm not going to visit it. Okay, so let's ignore it. So now from 4 neighbors is 5. Okay, so from 4 I can go to 5 in this 15. Okay, but here initially value is infinity. Okay, so I have to update it. Okay, so I have find the smallest value. So 4 to 5 I can go in what? I can go in 15. Okay, so here I'm going to write 15. Okay, so let's write 15 here. Then after that 4 I can go to any other place from 4? No, so here I'm going to write a same values. Okay, so here I'm going to write 10, here I'm going to write infinity, then here I'm going to write 45, then here I'm going to write 50. Okay, so now this is done. Now after this, what is the smallest value? So smallest value after this is this 15 now. Okay, I have already visited this 10. Okay, I don't need to visit now selected vertex 4. Okay, so initially I have selected vertex 1, then after that I have selected vertex 4. Now I'm going to select my vertex number 5. Okay, so here I'm going to write 5. Okay, 5. So now visit 5. So from 5 we can visit this 2. Okay, and this visit this node 2 we haven't visited yet. Okay, we haven't selected this vertex 2. Okay, so from 5 I can go to 2, and at which distance? Okay, from 5 I can move to 2. From this vertex is 5 I can move to 2, and see what is the value that I'm going to get here. Just 20, right? Okay, here one small mistake. From 4 I am moving to 5 now, so here I have to write 25 now. So starting point is 1 now, so 10 plus 15 is 25. So here let me modify it to 25. Okay, so this is 25. Now from 5 I need to see. Okay, so from 5 I can move to this 2. Okay, so total cost that I'm going to get is 10 plus 15 plus 20 is nothing but, so let's calculate, 10 20, 30, 30 plus 15 is 45. Okay, so 45, right? So I am getting the cost as 45. So here I am just going to change this 50 to 45. Okay, this is minimum value now, right? So once this is done, then from 5 I can visit any other node. I can visit 3. Now for visiting 3, 10 plus 15, 10 plus 15 is 25, 25 plus 35, 25 plus 35, if you do, you will get the answer as 60, right? But here I have given 45 now, so no need to update. Okay, 45 is the best solution. Okay, so here this is done. Then write the same things here, 20, 10, 20. I can visit 6 from 5, no. Okay, because arrow is pointed to this direction, so here I'm going to write just infinity. Okay, so now I have already visited this 5. Okay, I have already visited this 5, and now I have to find the smallest here. So smallest 45, 45 infinity. So let's select this one first. Okay, 45. So this is nothing but my vertex number 2. Okay, so here I'm going to write 2. Okay, so this is 2. Okay, this is done. Then from 2, let's see where I can move. I can move to this one. No, I can move to this 4. Yes, I can move to 4, but I have already selected this vertex 4. Okay, so I'm not going to traverse it back. Okay, so now, and if you want to traverse, you can check now. So here from 2, let's say you are going to move back. Okay, so what is the distance that I'm going to get? Okay, so here 1 to 10, 10 plus 15, 25, 25 plus 20 is equal to 35, 45, and 45 plus 15 is 60. 2 to 4 I'm getting distance as 60, but here it's already done now, so why I need to update it? I don't need to update it. Okay, so that is why we don't need to visit it again, which if we have already selected the vertices. Okay, so now same way I'm going to write the values here. So from 2 I can visit this 3. Okay, and what is the distance? So here 10, 15 plus 20 is going to give me 45. 45 plus 10, 55. So I don't need to update it. Okay, so I'm going to write the same things here. 45, then 45, then 10, then 20, then 25, sorry, and then infinity. Okay, I have already visited all this. Now what is the left out? This is the left out, so let's visit this. This is smaller than, right? So here I am going to write 3. Then for 3 I am going to visit. Okay, so I am not going to visit 5. Okay, if you can try, you can try to calculate distance. You will find that you will get the max distance, not 45, greater than 45. Okay, so here I'm going to write 45, 45, 45, 10, 25, and in the end we have infinity here. So we have visited all these except this 6. Okay, so let's say I have visited this 6 now. From 6 I am just going to 5 now, so no update. Okay, so here this is how I am going to fill the table. Okay, so I hope that you guys are clear. Okay, how this Dijkstras work. Okay, so now let's understand this problem with an example one. Okay, so this is giving me the minimum shortest path. Okay, this is giving me nothing but the minimum shortest path from start to destination. Okay, minimum, this is giving me just minimum, but in our case, but we need second minimum. So I'm just going to create 2 arrays. Okay, so in first array I'm going to create minimum, and in second array I'm going to add second minimum shortest distance. Okay, so now let's understand it with the example. Okay, so here n is equal to 5, and these are the edges. Okay, so here if I draw this, n is equal to 5, so 5 cities, and then there is one edge from 1 to 2, 1 to 3, 1 to 4. So 1 to 2, 1 to 3, 1 to 4, and then 3 to 4, and 4 to 5, 3 to 4, and 4 to 5. Okay, so this is bidirectional. Okay, so 1 to 2 I can also represent it like this, okay, 2 arrows. Okay, so this is just the same thing. Okay, so this is bidirectional. Okay, so now time is equal to 3 and change is equal to 5. Okay, so from 1 to 2 if I move, then time I'm going to take time as 3. From 1 to 3 if I move, I'm going to take time as 3. From 3 to 4 if I move, I'm going to take time as 3. From 4 to 5 if I move, I'm going to take time as 3. Okay, so this is the time for each edge. Okay, and change is equal to 5. Okay, so after every 5 minutes a signal is going to change. Okay, so here before proceeding further, I have to tell you one important thing. Okay, how this change will work. Okay, so now let me draw this single line. Okay, so here I'm just going to write times. Okay, so here this is 5, and this is 10, this is 15, this is 20, and here this is 25. Okay, so initially my signal is green. Okay, so my signal is going to green from this to this time period. Okay, from this to this time period. Then after that my signal is going to change to red. Okay, vice versa. So here I'm going to write R. Okay, then again my signal is going to change to green, okay, here in this part. Then my signal again will change to red in this part. Then again my signal will change to green in this part. Okay, so this is what's happening, okay, after every 5 minutes. Okay, so now from here let's derive one formula. Okay, so let's say okay, so here first let's calculate the shortest path. Okay, so how we are doing that? So from 1, let's say I move to this 4. Okay, so 1 to 4, total time I'm going to take is 3 minutes. Okay, so now in 3 minutes, so definitely I am somewhere here. Okay, I am here, and right now signal is green only. Okay, so this is nothing but 1, this is 2. So after 3 distance, okay, so I am somewhere here. Okay, here in this green part. Okay, so its signal is green. So from this 3 I can proceed to this in this 3 I move to this 4. Now I am at 4. Now signal is still green, so I can directly move to this 5. Okay, so total time here I am taking, okay, so total time here I am taking is nothing but 6. Okay, so see here, the figure on the left shows the given graph. The blue path in the figure on the right is the minimum time path. Okay, so see blue graph. So 1 and then 2. Okay, start at time 1, start at 1. So we started at this particular and then from 1 we move to 4 in just 3 minutes, and my signal is still green, so I can move from 4 to 5. So I move to 4 to 5 in just 3 minutes, hence the minimum time needed is 6 minutes. Okay, so I hope that this is clear. Okay, now this is done. Now what's happened, let's say from 1 I move to this 3. What is first? So to 1 to 3 I move, then I take 3 minutes. Okay, and I am somewhere here. Okay, I am somewhere here. Okay, so here let me mark this is white color. Okay, so I am somewhere here. Okay, now after this 3 I can move to 4 directly, right? I can move to 4 directly because I am somewhere here now in green part only. So here 3 to 4 if I move, I again took 3 minutes, but right now total time I have is 6. Okay, total time 6 minutes. So somewhere I am somewhere here in this part. Okay, I am somewhere here in this part. Okay, 6. Okay, so now I am, right now signal is red, so I have to wait until it becomes green, and it is going to become green after this 10, right? After this 10 it is going to become green. So here I have to wait for 4 minutes. Okay, 6 minutes. Okay, after 6 I have to wait for 4 minutes, and then after that I can move from 4 to 5. Okay, so now 4 to 5, again it is going to take 3 minutes. Okay, so 10. Okay, so I have waited till 10, and in the 10 I am going to add 3, so I am going to get the result as 13. Okay, so this is nothing but my second minimum time. Okay, so see here, the red path follows the path to get the second minimum time. Okay, so this path 1 to 2 and 2 to here third one. Okay, 4 to 5. So here start at 1, then 1 to 3, 3 minutes, time elapsed 3. 3 to 4, 3 minutes, time elapsed 6. Then wait at the 4 for 4 minutes because our signal is red. So now time elapsed is 10. As soon as it becomes 10, I can move from 4 to 5. Okay, in 3 minutes. So total time elapsed is 13, and this 13 is going to be my output. Okay, so now from here, see, so when I am going to say one thing here. So when my time elapse is 6, okay, so then I am at this somewhere here, right? So if I divide this 6 with my time, okay, so 5 period, okay, every time this period is of 5 minutes, 5 minutes, 5 minutes. Okay, so if I divide this with 5, then what is the output that I am going to get? I am going to get the output as 1.1. Okay, okay, this is done. That simply means that I am, this is one part, and I am in the second part somewhere here. Okay, 1.1. Okay, 1.1 here. Okay, so now I am just going to take the integer part. Okay, this integer part, and in this integer part, okay, this is 1.1 now. In this integer part I am going to add 1, which is going to give me 2, and I am going to multiply this 2 with this 5. Okay, that's this period. Okay, 2 into 5 is equal to 10. Okay, so it is going to give me the nearest time when my signal is going to turn green. Okay, so from here I have derived one formula. Okay, what is that formula? So that formula is nothing but, first I have to divide my time passed with the change value that is given to us. Then after that I am going to check if my signal is green or red. Okay, so here when I divide, okay, so let's say my value is 4 here. Okay, the value is 4 here, so 4 divided by 5 is going to give me 0. When my signal is here 6, okay, so 6 divided by 5, it is going to give me integer part. Okay, I have 1 only. Okay, when it is 7 by 5, then it is also going to give me 1. Okay, so in this part you will see that every time I'm getting 1. Okay, when it is 9 by 5, then again I am going to get as output as 1. Okay, 1 point something but 1. When it is in this part 10 to 15, let's pick any value, let's pick 12. Okay, so when I'm going to divide 12 with 5, then what is the result that I'm going to get? 5 2 is 10, so here 2. Okay, so here I'm going to get the this as the value, right? 2, so it is going to be 2 point something. So here it is going to 2, and here in this part it is going to be 3 point something. Here in this part it is going to be 4 point something. Okay, so from here one thing is clear, that every time when my signal is green, I am getting values in even number. Okay, even. Here it is green, so I am getting a number in even number. Here when it is green, I am getting a number as green. Okay, a number as even. Whenever my right is red, I am getting the numbers as odd. 1 here, then 3 here. Okay, so what I am going to do, first thing I am going to do is I am going to divide this time passed with the change. Okay, and then whatever the result that I am going to get, I am going to see if it is 1, if it is equal to 1. Okay, that simply means I am going to check if it is odd number. Okay, 1 or any odd number. Okay, so if it is any odd number, then simply means that it is a red light. Okay, then if it is a red light, then what I am going to do, then after that I am just going to uh, in this value, okay, in this value 1. Okay, in this value I'm going to add 1. Okay, and after adding this 1, I'm going to get the result as 2, and in this 2 I'm going to add the change. Okay, change value this 5, so I'm going to get the result as 10. Okay, so this is what we need to do. Okay, so I hope that this part is clear. Okay, so that's it, that's what we need to do. Okay, so in this problem we have to create 2 arrays. Okay, 2 arrays, and in one array I am going to store the minimum value, and in the second array I am going to store the second minimum value. Okay, so let's see how that is working. Okay, so let's understand this with example 1. So since the graph is bi-directional, so I have made the diagram like this. Okay, so to solve this problem, initially what I am going to do, so here this array, so in this array I am going to store minimum distance. Okay, minimum shortest distance, and in this array I'm going to store second minimum distance. Okay, so from I'm going to start from 1 now. So this is given in the problem statement, right? I'm going to start with this node. Okay, so here distance of this node to itself is going to be 0, right? And I am going to fill all the other values as infinity. Okay, initially all the values as infinity. Okay, before starting. So this is the second max distance. Okay, so here minimum is 0. Okay, I am storing the strictly second largest. Okay, so here I can't store 0, so here that is why I am going to store directly infinity here. Okay, all the values are set to infinity initially. Okay, so this is the first thing that we need to do. And in the priority queue, first since we are starting from my node 1, okay, this node, so here initially time is 0. Okay, initially here in min heap I am storing time and node. Okay, initially time is 0, time elapsed is 0, and node is 1. Okay, so that's what I'm going to store here. Okay, so now after that let's see what we are going to do here. So here in this time passed I'm going to start from this 0, and my node is 1. Okay, so from 1, what are the different nodes that I can visit? I can visit this 2, I can visit this 4, and I can visit this 3. Okay, so now let's do one thing here. From 1 I can visit the 2, I can visit 3, and I can visit 4. Okay, so from 1, if I visit this node 2, then what is the total time that I'm going to elapse? Okay, so first let's remove it. Let's remove the top element from my this main heap. Okay, so now after that what we have to do here, if I move from 1 to 2, okay, if I move from 1 to 2, then in that case time elapse is 3. So here I'm going to write 3, and after that I'm going to be in node number 2. Okay, this is done. 3 by 2. Okay, signal is still green. Okay, signal is still green because I am somewhere here. Okay, at 3. Okay, so from 1 I can move to 3 and can also move to 4 now, but here first let's update this minimum distance. Okay, so what I'm going to do here in this my minimum distance array, here instead of this 2 I'm just going to write what I'm going to write 3. Okay, 3 is the shortest path. Okay, so here I'm going to write 3. Okay, this is done. Now after that, from node 1 I can also move to node 3. Okay, so if I do that, then what I need to do? Okay, so from node 1 if I move to node 3, then total time that is going to be passed here is 3, and I will be at my node number 3. Okay, so here also let me update this to 3. Okay, so this is done. Now I can also go from node 1 to node 4. Okay, so what I'm going to do here, I'm just going to update this to 3. Time elapsed total is 3. So here from 3 I'm going to what node? I'm going to 4. Okay, this is done. Okay, 3 to 4, 3 time passed and I'm at 4 node. Okay, so now after that, once this is done, then after that what I'm going to do here, so now let me just remove this. So now I'm going to pop the top element from this priority queue. So let's say this 3 and 4 is in top. Okay, since this is min heap and based on these values, okay, these values I am sorting right, this value. So let's say if this is on top. Okay, so my total time passed is 3 and I am at this particular node 4. Okay, so now from this node 4, what are the nodes that I can pass? Okay, so from node 4 I can go to this one. From this 4 I can move to 3, and from this 4 I can move to 5. Okay, so let me just remove it from the top. Okay, so I'm checking for this one now. If I move to 1, okay, so from this 4 I can move back to 1 now. So here total time that going to be elapsed is 6, and then I will be at this node 1. Okay, so here see, in my this minimum distance, this is nothing but my minimum distance array, and this is nothing but second minimum distance array. Okay, so in my minimum distance array this value is already 0, right? And here time elapsed is 6 and here time elapsed is 0. So why do I need to update my minimum distance? I don't need to update my minimum distance. So what I'm going to do, I'm going to check second minimum distance. In second minimum distance value is infinity. Okay, so now I have to update this infinity with this 6. Okay, so I have updated to 6 and now I am at node 1. Okay, since this is my main heap, so I have to add this 6 one in the bottom. Okay, so let me just update this main heap. So okay, so I have updated this 6. Okay, so now we have already visited this node 1 from 4. Okay, so let me just remove it. So you guys are clear now why I'm writing 6 here. Okay, so 1 to 4 I can go directly. Okay, 1 to 4 if I go directly, then I am getting this total distance as 3. But here what I am doing, from 1 I am moving to 4, and then from 4 I am moving back to 1. So 3 plus 3 is 6. That is why I am writing 6 and again at node 1. Okay, now from 4 I can also move to 3. Okay, so let's see if from 4 if I move to 3 back. So from 4 if I move to 3 back, then total distance that I am going to get is time elapsed that I am going to get is 6, and I will be back at this 3. Okay, so 6 and here value is time elapsed value is 3 here. Okay, if I move back to 3, okay, this is 3 now. If I move back to 3, value is 3, but here I'm value is 6 now, so I don't need to update it in my minimum distance array, but I have to update it in my second minimum distance array, because here this value at node 3 is infinity. So let me update it. So here I have updated it to 6, and I have to put this 6 by 3 in my main heap. Okay, 6 by 3 I have added it here. Okay, let's see. Okay, this is done, and now let me just remove it. Now from 4 we have already visited 3, so now let's move from 4 to 5. So okay, if I move from 4 to 5, then 4 to 5 my total time elapsed will be 6. Okay, because I have already visited 1 to 4 now. Then from 4 I am moving to 5, right? So total time elapsed is 6, and I will be at node 5. Okay, 6 5. So here initially my minimum distance array is infinity. This value is larger than this 6, so I am going to update it to 6, and I am going to push this into my main heap. Okay, 6 and 5. Okay, in the priority queue I am going to add 6 5. Okay, this is done. Okay, so from 4 I have visited all these nodes. Okay, now you will see that in top of my this priority queue, this value is there 3 by 3. So let's extract that. So here this value is 3 and this value is 3. Okay, time passed is 3 and the time elapsed node is 3. Okay, so from 3 I can move to 1, I can move to 4, and I can move to 5. Okay, total 3 type of scenarios. Okay, so let's say if I move from 3 to 1. Okay, so time elapse is already 3 here. Okay, 1 to 3 is already 3. Now from 1 I am moving back to 3. Okay, so total time elapse will be 6, and here node will be 1. So 6 1. So here this value 0 is minimum, so I don't need to update my minimum distance. Here this value 6, and here this value is also 6, so I don't need to update because this is already there now. So that's it, so we have to do nothing here. Okay, right? So now from 3 if I move to 4, so from 3 if I move to 4, then total time elapse will be 6. Okay, 1 to 3 and then 3 to 4, so total time elapse 6, and I will be at node 4. Okay, so 6 and 4, so 6 and 4 minimum distance is here 3, and here it is 6, so I don't need to update my minimum distance array. In second minimum distance array, the distance is infinity, this time elapse is infinity, and here it is 6, so let's update it. Okay, so I'm going to update it to what, 6. So I have updated to 6, and here 6 4 is there, so I'm going to add this 6 by 4 in my priority queue. Okay, so now this is done. So from 3 I have already visited 4. Okay, so let me just remove it. From 3 I can visit why I am writing 3 to 5. Okay, so no, we can't visit this 5. Okay, so let me just remove it. Okay, so by mistake I have written here. Okay, now this is done. Okay, and we have already visited this 3 by 3, right? Now I have to visit 3. I have to visit node 2, and where time elapsed was 3. Okay, so from 2, what are the nodes that I can visit? I can visit just 1. Okay, so if I just move to 1, then I will see that total time elapsed is going to be 6. Okay, 1 to 2 and 2 to 1, total time elapsed will be 6, and I will be back to 1. And here I need to add 6 in 1. So here minimum distance value is 0, so I don't need to update here. And here second minimum distance value at this particular node is 6, so I don't need to update here. So 6 1, I'm not going to do anything. Okay, that's it. So I have already visited 3 by 2. Now we have to visit 6 by 5. Okay, so time elapse is 6, and we are at this node 5. Okay, so now this in the red signal area. Okay, so I have to simply write 10 here. Okay, so here time elapse I'm just going to update as 10. Okay, time elapse is 10. Now I am at this 5. So from 5 I can only move to what? I can only move to 4, right? So here 10 plus this 3 13, time elapse is 13, and I will be at 4. Okay, so here at this 4, you see we have this 6, we have 3 here, so I don't need to update, and we have 6 here, I don't need to update. So now why do we need to update? Okay, we have already filled the minimum distance, second minimum distance value with the smallest value in this 13, so I don't need to update. Okay, so now this is done. 6 5 we have already visited. Okay, let me remove it. Now we have to visit 6 4. Okay, so time passed is 6, and we are at this node 4. Okay, so what we are going to do? So let me just remove it first. Okay, so now see carefully. So now from this 4 I can visit to 5. Okay, since this is 6 now, so here I have to write 10 directly, right? Because this is red signal area, right? So here I am going to write 10. Okay, this is the first thing that we need to update. So now in this 10, if I move to 5, now from 4 I can move to 5. From 4 I can also move to 1 and 3. From 4 I can also move to 1 and 3. Okay, but let's say first I'm moving 4 to 5. Okay, so you can check with the 1 and 3 also, but let's say if I'm moving from 4 to 5. Okay, so now in 10 if I add this 3, okay, 13, then I will be at 5. Okay, so here see at this 5 we have 6, and now we get 13. Okay, so this was infinity, so I have to update it. So I am going to update it to 13, and here I'm going to add 13 at this particular node 5. Okay, and so on. We have to do all this similar thing, and we will find that we will not find the minimum value than this 13 in the second minimum distance. Okay, later on. So just follow all these processes one by one. So you will find that in second minimum distance array, this is the value at this particular node. Okay, second minimum distance value. Okay, and we have to do that only. Okay, so if we reach the node n, that is nothing but node 5, and it's the second time. Okay, first time we have visited, then we get 6, and in the second time when we have visited, then it is 13. Okay, then we have to just simply return the result. Okay, that's it. Now let's move to the coding part. So first thing that we have to do in our code is to represent the graph using an adjacency list. So what I'm going to do here, I'm going to create one list of integers. Okay, so once this is done, then I have to add all the nodes, okay, what that I have from 1 to 5 in my graph. Okay, so for that I'm just going to write one for loop. Then after that we have edges given to us, right? So we have to just connect the nodes. So okay, so for that I'm just going to write one for each loop. Okay, so see here, we are iterating over all the edges one by one. Okay, so since this is a bidirectional graph, that simply means 1 to 2 there is one edge, and 2 to 1 also we can go. Okay, so that is why I am taking u and v value. Okay, so from this particular edge, let's say 1 and 2, 1 is nothing but u, this is v. Okay, so in my graph I'm going to get this key, okay, u, and in this particular key I'm going to add this v. Okay, so this is what we are doing in this part. Okay, now in the next step we have to initialize the distance arrays for the shortest and the second shortest time. Okay, so for that I am going to create two arrays. So let's name as d1. D1 is nothing but my minimum distance array, and d2 is nothing but my second minimum distance array. Okay, and I'm going to feed all the values in my both the arrays as integer dot max value. That simply means infinity. Okay, okay, so see here we have created both the arrays, right, d1 and d2, and since we have nodes from 1 to 5 now, and it is inclusive 1 and 5 as well, so that is why I am giving n plus 1, okay, size here. Okay, so once this is done, then our step 3 will be a priority queue for Dijkstra's algorithm. Okay, so for that I am going to create one priority queue, and in the starting I am going to add my time elapsed initially is 0 now, so in starting I'm going to add 0 and my source as 1. Okay, node 1. Okay, so in this way I'm creating my min heap, right? So now let's do that. So see here in this part we have created the priority queue, right? And we are creating the int array type, right? So here we are adding two values, right? One is going to be my time elapse and one is going to be my node. Okay, two values. Initially I am starting from this, so initially my time passed was 0 and starting node is 1. Okay, so these two values I have passed in this part. Okay, in this one. So how it is working here, since this is a main heap now, so let's say if there are two arrays a and b arrays, okay, so I am comparing them based on their, okay, these are nothing but parameters. Okay, two parameters are there. So let's say one parameter is like this, 3 by 1, and one parameter is like this, 6 and 1. Okay, so these are two arrays. Okay, that's it, two arrays. So I am just comparing their first values. Okay, so here I am comparing first value a of 0 minus b of 0. Okay, so if it is true, then we are good. We are just going to write first a value. Okay, that simply means this value, and then this value. Okay, since this is a main heap based on these values. Okay, 3 and 6. Okay, so that's the simple meaning of this one. Okay, so once this is done, also as you see that here I am starting this with 0 and all other values were in infinity set by us, right, here already. Okay, so now let's update this to 0. Okay, so now I'm going to do that. Even array at index 1 is equal to 0. Okay, so this is index 1. Okay, index 2. Okay, this is how we are doing, right? So now after that we have to run one while loop, and I have to run this while loop until my priority queue is not empty. So once this is done, then we have to pop the top value from my min heap, right? So here I am just going to create one array. Let's name it as current. So here priority queue dot poll. Okay, so it is going to poll that top values. Okay, which is in array format only, right? Containing what distances, time passed, and my node. Okay, so now after that my time passed is at first index. So here I'm just going to create one variable time passed, two variables time passed and node. Okay, so here I'm going to write time passed is equal to curve of 0 and my node is equal to curve of 1. Okay, this is done. Then after that we have to check here if we reached node n and it's the second time, then we have to return the result. Okay, so let's write this base condition, return d2 of n. Okay, now after that we have to calculate the wait time based on the traffic signal. Okay, so I have explained this part here, right, somewhere here. Okay, so how we are driving this from a 6 divided by 5, then what we get, then in that we are going to add 1. Okay, then what is the result that we are getting? In that I am to multiply the change. Okay, then I'm going to get one value 10. So 10 is nothing but the where my signal again converts to green. Okay, so I'm going to write the code for this particular part. Okay, so here int, let's create one variable mult is equal to time passed. Okay, so here I have to write time passed, and I have to divide it with what, with my change, right? So once this is done, then after that I have to check if the value is odd or even. So for that what I have to do, if this value mult, if I do the modulus of this with 2, and if I get that this value is equal to 1, that simply means that is the odd number, that simply means that read right. So what I have to do, so in that case time passed is equal to change. Okay, what is the change value that I have, and I have to multiply this value with what, this mult value. Okay, mult, and in this value also I have to add 1, right? So this is going to be nothing but my wait time for the green light. Okay, so I hope that this thing is clear. Okay, so this is what we are doing here, right? Here this become 10. How it becomes 10? So this is the code for that one. Okay, so time passed is equal to change into mult plus 1. Okay, that's it. Okay, now last step that we have to do is nothing but process the neighbors. Okay, so now let's do that. So here what I have to do, I have to run one for each loop for int neighbor. Okay, and I have to check in the graph now. So graph dot get that particular node. Okay, for that particular node we need the neighbors, right? So here inside this I have to check few things. Okay, so first thing is that I have to get the new time. What is the new time? So int new time is equal to my previous time, that is time passed. We have to add the time. Okay, so once I get this time, then I have to compare this time with the times that are already there in my two arrays d1 and d2. Okay, so if d1's array for that particular node, the time that is already there is smaller than the new time pass, then I don't have to add it. Then I have to compare that with my second max distance d2 array. Okay, but if it is greater than the new time pass array that I am getting, then I have to update that. Okay, so I'm going to write the code for the same thing here. Okay, so here see, if in this part, if d1 of neighbor is greater than new time, okay, then what I have to do, I have to update my d2 to neighbor as d1 of new neighbor and d1 neighbor as new time. Okay, so this is what we are doing, right? And in the PQ I'm going to offer this. Okay, so simple means na, let's say here in this is my d1, okay, and this is my d2 array. Okay, so initially this value is infinity and this value is 10. Okay, so let's say new time pass, that value I am going to get is 3. Okay, so first I have to compare this with d1 na, this one, this value 10 is greater than this 3. Okay, so now I have to update this with 3. Okay, so let's say I have updated it with updated this with 3, then this 10 will go to this place now, then this will become my second max. Okay, that's the simple meaning of this part. Okay, and as if, okay, if this condition is not satisfied, as if I am going to check if d2 dot neighbor, okay, if it is greater than my new time and d1 of neighbor is not equal to my new time, then my d2 dot neighbor, okay, is going to become my new time, and here I have to add pq dot offer. Okay, that's it. Now in the end, once this is done, then I have to simply return -1. That's it, my code is done. Okay, now let's try to run the code and see if there are any code issues, then we will try to fix that. So yes, there are some issues, let's try to fix them. So line number 18 basically I am getting the issues, and line number 19 we are getting some issues. So now fix line number 18 and line number 19. Okay, so let's move to that. So here in line number 18, when we are using this priority queue, so see here code priority queue, and here int, and here pq is equal to new priority queue, and here ab. Okay, all this should be in between this one now. Okay, so this is done, and here also I have missed this. Here it should be array now, so here I have to add the values like this now. Here array values. Okay, so this is done. Now let's try to run the code and see if there are still any code issues. So all the test cases has been accepted. Now let's submit it. So see, our solution is accepted, right? Okay, so I hope that you guys are able to understand today's problem, and if you guys still have any doubts, then please feel free to ask in comment section. Till then, keep coding and keep practicing. Meet you guys in the next video. Thank you. Bye.